All right. Good evening, good afternoon, good morning, ladies and gentlemen, wherever you are. We are live and all the day is here. This is the first and the beginning of our Advanced Ethical AI Webinar Series 2024 being hosted by HiPIC, High Performance Computing Lab in the University of Nigeria, Soka, Nigeria. And we are going to be having quite a lot of mind-blowing talks, different talks in machine learning, data science, governance or data governance, in ethical science and responsible AI. So it is well packed for this month. And I expect that you make use of it if you're a student, researcher, or a stakeholder in the industry. It's an opportunity for you to come have a network time, network with experts in this area and have an opportunity to ask questions, have your answers given to you, or you can actually write an email to contact the presenters to be able to have some feedback from them. Right about now, we will start. First of all, we would like to bring up the director of the lab, the person of Professor Collins Sodano, to actually give an opening speech before we start. Professor Sodano, if you're there, please, I will hand the podium over to you.
Thank you very much, Dr. Bokri, for the introduction. And I welcome every one of us who is joining us for this first webinar series. A little about HiPIC, High Performance and Intelligence Computing Lab, is based at the University of Nigeria. It has grown from a research group to a well-established lab with multidisciplinary collaborations. We have people in the biological sciences, have people in the physical sciences, people in engineering, and all that. And our research cuts across different domains, such as agriculture, healthcare, computer IT, and the rest of them. One of the flagship of our research lab is our data set, which we created during the Lacuna Fund project that is readily available at the Cargo Data Repository for machine learning community and for researchers. And I must tell you that since 2 years, it has been up. We have had over 1,000 or going to 2,000 downloads. And a lot of people have been commending the work, and we are still working. We're still coming up with a new data set, an improved version of what we have out there. So our research cuts across different areas. We have also in our group postgraduate students as well as lecturers and industry experts. So I want to thank you for coming today. I believe that you are going to enjoy today's webinar. Our speaker, who will soon be introduced, is well versed in the topic of today. And subsequently, for the next 3 weeks, you are going to be introduced into so many areas of ethical AI and machine learning. So I want to say welcome once again. So please listen attentively and gain something. Thank you so much. Dr. Bokri, over to you.
All right, thank you very much, everyone. So I'll go ahead to introduce our speaker for today. Learning and data reprocessing is Dr. Chinedu Nwoye. Dr. Chinedu Nwoye is a postdoctoral research fellow at Kama IHU Strasbourg, where he leads pioneering effort in surgical generative AI. He earned his PhD in computer vision from the University of Strasbourg, France, and his master's degree in artificial intelligence from the University of Southampton in the United Kingdom. His research interests include deep learning and its application in surgical assistive interventions. He is the principal organizer of the MICA Endoscopic Vision Biomedical Challenge on Colic triplet, a groundbreaking initiative that models surgical activities through the representation of the two action anatomy relationship. In addition to his research contributions, Dr. Chinedu served as an area chair for HiPIC-High 2024 and is a co-organizer of the NURIPS workshop on large models meet surgical data science. Currently, Dr. Nwoye also serves as an adjunct lecturer in Signet Vacatarian at the University of Strasbourg, where he shares his expertise and passion for advancing the field of surgical AI. His leadership and innovative research continue to push the boundary of what is possible in medical technology. Aside from academic and career and research, Dr. Nwoye is a co-founder and chief AI officer of Betavoid. The office designed hours of Lavuza electric cybercars. Anyways, I'm not a French person. These words are very French-like. Ladies and gentlemen, Dr. Chinedu Nwoye.
Thank you, Dr. Blessing Ogbueki, for that kind introduction. I'm happy to see a lot of people that I know before and the new faces. We are going to get to know each other through this program, and I'll be happy to present my insights working in deep learning, especially in the field of surgical data science. So I'm going to go ahead to share my slides. I want to be sure that everyone is seeing my slide.
Yes, we are seeing your screen. Just a moment, I'm just passing an information. So audience, if you have any information, any question, you could actually type it on the chat box. We'll read the questions out after the presentation. Or if you have any concern that you need us to clarify, or you need the speaker to clarify or stuff like that, you can actually type it on the chat box so that we can respond to that as we finish. Over to you, Dr. Chinedu.
All right. So thank you all. Welcome to today's talk on fundamentals of machine learning and data processing. I am Dr. Chinedu Nwoye, adjunct professor at the University of Strasbourg. Today I'm going to be talking on the fundamentals of machine learning, and I don't, disclaimer, I don't work currently on machine learning and data processing. I basically work on deep learning, which is another step ahead of machine learning, but machine learning being the base, it is important to talk about it before talking about deep learning. So I want to start this talk by introducing us to the field properly. And this is usually the question I get from a lot of people. What is the difference between this machine learning and what we know as artificial intelligence or neural network, or even the deep learning, which I say that I'm working on? So artificial intelligence, to understand it, we need to go back to understand what is intelligence, which is the ability to learn, understand, and apply our knowledge to solve problems and adapt to new solutions. So what a child does, and it enables the child to move to a new situation, which is usually an improvement from the existing situation, is the use of natural intelligence. Then in this natural intelligence, what we notice that the child is doing by applying intelligence is decision-making and the ability to solve problems. When this is done, we can say that the child understands the problem and the child is learning from the problem and the child is solving the problem. So what is artificial intelligence? It is simply making AI system or making computer system to mimic that decision-making ability or problem-solving ability of the human brain. And we have a lot of applications of this in the real world, such as object detection, content creation, even in the medical field, like diagnosis, drug discovery for those in the pharmaceutical, also in the security for surveillance. We can also see it in the biological research where we use it for gene and protein folding. Useful to those in the financial market because we can use this for financial analysis. And for those in manufacturing today, we have the use of robots, which is based mainly on the use of artificial intelligence. Beyond this, we can go towards a more complex scenario like autonomous driving, or including augmented and mixed reality, which are advancing field of artificial intelligence that we are glad to be witnessing these days. Having said this, now it is interesting to look at how this AI is divided. The AI has a lot of subfields like machine learning, expert system, natural language processing, speech recognition, and the rest of it. But today we are going to be focusing on one, which is the machine learning. So what is this machine learning? Machine learning here, we simply want to make a system that mimic the decision learning process, which is the AI, but then we want to make the system that is going to learn this from data. So machine learning is about to make machine to drive its knowledge by observing several examples. There are key points that I have put in bold here for you to note because these are important in understanding what machine learning is. The first one is drive. It needs to drive its knowledge. That process of driving its knowledge is known as learning. The second thing is the knowledge. It needs to build the knowledge about the problem. This is what we know as algorithm. In normal computing, we know about algorithm sets of rules, but we're going to see how machine learning algorithm is different from the traditional programming algorithm. Then another key point is observing. We have given it the data to learn from, so we allow it to observe. We are not telling it what to learn and what not to learn. It observes and chooses what to learn. So it is a self-training process. It learns on its own. And it learns this from several examples. This example is the data which we are giving it. Now over to neural network. If we want to understand neural network, we need to go back to biology, the human brain, how it processes information from what we know as the neuron in the brain, which compose of the cell body, the axon and dendrite, and all these communicate with the nucleus, receive response signals, and they process the signal to give a response. So neural network is simply a creation of this neuron artificially. So we call that artificial neural network, our way of making the biological neuron to function like human brain, both in the structure and the way the data is flowing. Now to deep learning. What is deep learning? The interesting area, the field that is making a very big wave these days. It's comprised of using several of these neural networks to make complex decision making. Now we have seen how all these are interwoven, from artificial intelligence to machine learning to neural network, and neural network to deep learning. But today we are going to focus on the fundamentals of machine learning. And the structure of my presentation will go from the introduction of machine learning to data and data processing, and discussing what machine learning algorithms are and the model that we derive by training a machine learning algorithm. And we can see how we can use this model to make some inferences, evaluate our inference, and make model selection, and some examples of applications of this in the real world. So at the end of the presentation, I expect that you will understand the basics of machine learning, familiarize yourself with the types of machine learning, the importance of data in the machine learning, and gain some knowledge on data pre-processing techniques. I also want you to understand few things about feature selection and engineering insights. I would also want you to also be aware of how models are evaluated, the techniques we use, and why we use them. And I'm also going to expose you to the real-world applications of machine learning and throw some insights for us to be aware of the future trend of this machine learning. And hopefully at the end of the presentation, you'll be encouraged for further learning in this field. So what is machine learning? A simple book definition of it says that it's the field of study that gives computer the ability to learn without being explicitly programmed. This is given by Arthur Samuel in 1959. But from what I have said so far, it will be easy for you to drive that machine learning is simply a science or art of programming computers so that they can learn from data. And I keep emphasizing on learning from data because this is what makes it machine learning. And I'm going to spend a lot of time to explain what I mean by learning from data. So at the layman's level, I would say that it's simply making a computer that can understand the real world from example data and they possibly solve it. Even if it doesn't solve it, the most important thing we want to achieve with machine learning is ability to understand the real world from example data. But problem solving using what is learned from the data is a way to demonstrate that the machine actually understood the real world. Because if you are a student and you claim to understand a field, if you cannot apply it to solve a problem, we are in doubt if you actually understood. So the problem solving aspect of it is a proof that the machine understood the real world. But this is not the only time we are talking about using computer to solve problems. The traditional algorithms that we have are being programmed today. We can have C++, Java code written to solve real-world problem. Yes. So why are we not talking about machine learning? Is it not the same as the traditional programming? No, it is not. Though the traditional programming can solve real-world problem, they rely on something we call algorithm. Algorithms are a set of rules that solve problems. What this means is that for you to solve a problem, you need to manually write the algorithm. The algorithm will show the sequence of steps that must be taken to arrive at a solution given a problem. Now, where the problem comes in is, what if you do not know the rules or the sequence of instructions to solve this problem? What if this algorithm is undefined, for instance, a very complex problem? How would you program the real-world solution? What if the data you are trying to use to solve this problem is so complex that you cannot program the steps to solve it? For instance, understanding the gene sequence, understanding the protein folding, or even recognition of cancer. How would you be able to write the algorithm for this? So another case is when the patterns are so complex and the relationship between them is equally complex. So you can't drive this relationship by just writing an algorithm. There will not be just if then do that will lead to a solution. Or maybe there are some level of uncertainties, something that is not very sure, that if this happens, this must happen. There are some level of probabilities. So we call this fuzzy logic. So at this stage, you see that algorithm will fail. Another thing is when you finish writing your code based on a static algorithm, how would it generalize on new data or new case scenario? Or how would it improve what it has learned with new instances of data or new situations? So these are reasons why we have something we call machine learning. Machine learning comes to overcome the static nature of writing a program and building a traditional programming code that can solve it. A very good example here is, if I give you this solution, maybe this is one of the quantitative reasons that students get from school. You have the first two blocks with the solution. So the problem is the M block, the matrix, and the answer is the A. So what you need to do to solve the last one is to understand the relationship or the operations that must be performed with the data in the 4 blocks to give the answer. Now, this is going to take you time to figure it out. And then when you figure it out, you know what happens with block 1 to block 2 to block 3, 4, what type of operation, and you'll be able to drive this solution. So this is what we do with traditional programming. We first create the rules, which is the algorithm, and then we write the code. And the algorithm is simply this. Sometimes we are faced with a real-world problem that is not just 4 blocks of matrix, which is 2-dimensional. Some of the word problems are n-dimensional. They can go into thousands of dimensions that you cannot even comprehend it by writing it down. So when we talk about machine learning, what we do is we define the algorithm without knowing how it is going to work. For instance, A is the summation of a weight. The weight is the brain, the knowledge, what is learned. That is what the algorithm understands. And the matrix is the input. And then we build our machine learning program to learn the algorithm. So it comes up with a weight. That weight, you don't need to sit down to figure out the rules. You just apply the weight to any given data and you get a solution. So this is how machine learning works in simple terms. So the difference between the two is that the traditional programming takes in data and algorithm and gives you an output. That data is what you have to feed into the machine, and the algorithm is what you have to write that define the steps to solve the problem. But in machine learning, you don't have to do this. You just give the model the data, and it gives you the algorithm. For it to give you the algorithm at the beginning, you need to give it the data and the solution. So the solution is the output. By observing the data and its solution several times, the machine reason about it and figure out what should be the algorithm. So what the machine gives you is the algorithm. Now you take that algorithm and apply it to your new data, and you get an output. So back to the concept of learning. What is learning? A simple definition of learning says that it's about improving your performance through experience at some tasks. And this is very important research goal for artificial intelligence. Without improving performance, there is no need for AI. So a learning, we can say that a computer program has learned if from experience with respect to some task that you've given to it, that the performance measure is, when you measure the performance, it improves with more experience. So this definition was given by Tom Mitchell in 1997, and it has been pretty much been used to define what learning means. So if I put this on the learning curve, it will simply mean at the beginning, there is a slow beginning to learn, which means you are beginning to observe some experience, some examples, some task. As the experience increases, you accelerate with a steep in your learning curve. And with much, much, much experience, you get to a level we call the proficiency, and then you could be able to do anything. At certain step, the performance plateau, that is when you become probably in the academic a professor. So we don't expect you to be something bigger than the professor afterward. So we hope that our machine learning moves up to that plateau level when we can be confident in its predictions. So a simple example I will give with this, or a more complete example, is if you are making a model that should predict the traffic pattern at a busy intersection. With historical data, is gaining some experience. And we can measure the performance of that model by its accuracy in predicting the future traffic pattern. And if this is done, we can say that the model is learning. Let me give you a brief timeline of machine learning over the time. It started a long time ago with some computer scientists coming together to think of how to document or to automate the process of writing algorithms so that they don't have to write it and they can use the machine to solve problems. And in 1805, linear regression was born, which was developed by Adrian Marian Jejon and his colleague Carl. Then the linear regression model was there to learn a trend or a pattern that could fit new sample data. And then in 1957, there is a perceptron. A perceptron was a more simulation of something that looks like the human neuron, and it was used for binary classification task. After then, we could see that we can actually train a machine that mimic the human brain. But then, how it is trained is by weight updates. So we want it to learn in a way that is similar to the way humans learn, by reward and punishment. And that is what gave rise in 1959 to what is known as reinforcement learning. Here, we have some agents that we allow this agent to learn by making some decision, and we evaluate this decision by either giving it a good reward or a penalty for bad decision. In 1964, the support vector machine was born, and this is one of the most powerful machine learning technologies that has been ever invented. So it first shows its progress in handwriting recognition, and it was also used for phrase dictation and every other thing. Support vector machine comes with the principle of learning a hyperbole, which is like a decision boundary that separates data points. And it does this so nicely by creating a decision boundary that separates these data points based on a pattern that classifies them to a particular categories. After then, the idea of training a model by updating the gradients, the weight of the gradient, was born, and we call this back propagation of the neural network. That was in 1985. Then there is boosting algorithm in 1990, which use a kind of ensembles to learn this. And then there is random forest, which is built on decision trees that is similar to what we have with our if-then-loop traditional programming of algorithm. But then the rules are also learned by the machine. In 1997, we were graced with advancement of machine learning to deep learning with the introduction of convolutional neural network, recurrent neural network, and the LSTM. And this deep convolutional network get its, I could say, it get its place in the field of artificial intelligence with what is done with image recognition using ImageNet, led by one of the godfathers of AI, Geoffrey Hinton, in 2012. At the same time, a model known as AlexNet was born, and also we know about one of the genius in the field, Yaran Kun, who also proposed something called LeNet at December 2012, and they participated in a competition with the ImageNet organized by Stanford University. Fast forward in 2014, there is generative adversary network where we can generate samples of our own data. And this was led by Godfellow. And today, generative AI is taking over the world. Some of the things in combination with what is recent with the transformer network, we can see models like ChatGPT, which almost everyone is using now, and we can demonstrate with this ChatGPT that machine can actually be intelligent. So to go in to discuss the machine learning more fundamentally, we need to understand the different components of machine learning. The first and the most important one is the data. And then there is algorithm and the model. At some point, we can merge the algorithm and the model together, but I choose to separate them because I want to derive some salient point from both of them. So let's go on to the data. For the data, usually everyone knows data is raw information that you have to process. In terms of machine learning, it is the raw information that we use to train our model. But my question is, what is really data to machine learning? Data is more than what we think it is. The difference between a big company, a big machine learning company, and a small machine learning company is not the model that they have. It is not the machine learning algorithm that they are using, but it is the data that they have. Even the biggest advance in AI, maybe ChatGPT and the rest of them, can be programmed overnight by someone who learns how to do it, but cannot be trained to have the proficiency of ChatGPT because of lack of the data at which the model is trained on. So data is very important. And so I try to give some of this as the metaphor of data in machine learning. The first is raw material. See data as a raw material. Data is the raw material which, when processed through algorithm, is transformed into variable outputs, just as you have the raw material that you turn into finished product in manufacturing, like crude oil to petrol. See data as the foundation of knowledge. Data is the primary source of knowledge from which model learn their patterns. It is the foundation which the model learns the correlation between features, or where the model gain insight. Without data, there is no experience for the model to draw from. See data as a fuel for learning or a nourishment. It's just like food that provides energy for the living being. So data provide the necessary input for machine learning models to grow and develop by learning from patterns. You can also see data as a teacher. In a type of machine learning known as supervised learning, data alongside with what we call the labels, which I will explain later, act as a teacher that provide examples and corrections, helping the model to learn from the correct output for a given input. See data as a blueprint or instruction or guide. Data guides the learning process. It is the data that instructs the algorithm on what pattern to learn and generalize on. Data is like the blueprint that defines the structure of the model. It defines the pattern in the model, which in the data, which the model should follow. So every information that you see as a blueprint is in the data. See data as a mirror. Data reflects the underlying pattern and the characteristics of real world. The way you see yourself in the mirror is the way machine learning sees the world through data. See data as a map. It provides the pathway for your model to navigate. It provides the pathway for the model to learn the relationship, the trend, and the association in the real world. You can also see data as a catalyst. Data acts as a catalyst in machine learning. Yes, it is the data that sparks the learning and the creation of model that can predict, that can classify, or otherwise make decisions. Data is the library or the comprehensive collection of information from which your model can read and learn from. Each piece of data adds value to your model's understanding of whatever concept that you are trying to make the model to learn. Data is also the lens through which a model can learn, can view, can understand the world. The reality and the quality of this data will affect the accuracy of your model, and it will also define what the model see and interpret as pattern. Data can also be seen as a bridge because it provides the connection between the real-world phenomena and the machine learning models. It is the data that allows the model to understand and interpret the real-world situations at hand. In terms of dynamic data, data that change over time, it gives that connectivity to the model to understand the change in the data and as the change in the world. So I would also say that the data is the heartbeat. I actually prefer to call the data the heartbeat because data is like the vital and the central of machine learning, just like life it is to you. Without data, machine learning model is dead. Data need to be continuously fed to a model, especially in real time, for it to be alive and keep making a prediction. The moment a machine learning model is not receiving data, it is as good as dead. So, having seen all this, I want you to look at these pictures and you begin to understand the powers in data. Imagine you have access to all this. You have access to all the medical record of everybody. You have access to everything that is possible in any of the search engine, Google, Yahoo, whatever. Everything that you can find in any social network, they are all data. What everybody have posted, what everybody is arguing, what everybody have commented, the information we share and discuss on Quora, what is in different e-shopping platform, Amazon and the rest of them, what people derive from research, the information that are contained in different textbooks, whether e-books or physical copies of books in different disciplines, every information in Wikipedia, what you have in different companies' record, in different offices, or the information behind the transformation of raw material to product, what every company have. If you have only the data that is behind Coca-Cola, you have your own drinks. If you have the information behind Innocence car manufacturing, you have your own car plants. Imagine the data behind financial markets. If you have it today, you become the richest man in the world because you can predict the market, know when to buy stock and when to sell. Just imagine you have every forbidden videos of everyone, all the information that is with the governments, your passport information, the database of maybe United States is with me, for instance, or we have access to what is with the intelligence unit like CIA or FBI, or let's not even think about it that you have the data of different nuclear weapons. So you could imagine the power in the data. So these are the things that we try to take and feed into something we created, and we allow that to explore that data and learn from it. So this is why machine learning is a very powerful field. How much data is actually created every day? I did some research and I figured out that actually in 2023, about 328.77 million terabytes of data are created every day. And 181 zettabytes of data is expected to be generated by 2025. So that is like 0.45 zettabytes daily. And around 53.72% of the internet data is created through videos. So I looked at the platform that actually gives us most of this data. Top is WhatsApp. Every day I get people to share some things and they say share it. If you don't share it, this will happen. We're actually sharing data. It takes about, for you to share 480p video on Twitch, you required 0.4 gig or 0 to 0.5 gig of data per hour to do so. But you could also see how much of information are being shared. More like 2 billion videos are being watched by users of Twitter just in one day. So it takes terabytes of data to share message on WhatsApp alone. And around 361 billions of emails are sent out there every day as of 2024. So it's an equivalent of 0.0001335 megabytes of data that is being sent out in one text message. So when you look at this, we are accumulating a lot of data on a daily basis. When we look at this by data centers that we have around the world, the United States leads with more than 5,000 data centers, which is times 10 you can find anywhere in the world, followed by Germany with about 522 data centers. And we have in the third position, United Kingdom, followed by China and the rest of them. And I hope by this, we will be able to start building data centers that we can use in our own home soil in Africa. Now, this is the list that I made. I got from the internet on the number of data centers that are being used over the world. And surprisingly, I could not find any African country there. So it shows how much we are missing out in terms of the data that are being shared all over the world. But one thing that surprised me, or we should be scared of, is that the global data creation is actually about to explode. At the time it's about to explode, we are heading to 1 terabyte of data by 2025. That is 1 billion of terabytes. 1 zettabyte is 1 billion terabytes of data. This is too much. And at this stage that the data is about to explode, we still not have enough data center in Africa. So let's look at the forms of data that we have. First is the direct and indirect data. This will help you to understand where you are actually contributing data. The direct data is the data that you are the primary generator, the data that you actually get from people through questionnaire, interview, observation, and the indirect data is the one that you get from mainly from the internet. And we have the static and dynamic data. The static data, the data that you've collected, it doesn't really change. Dynamic data is the data that change over time. It is not what it is today that it will be tomorrow. We have the raw data, the data that you keep in the original form, and we have the derived data, the data that you have generated from the raw data, maybe through experiment, through analysis. And we have the structured data and the unstructured data. The structured data is the data you have organized in a particular format for ease of use. And this is mainly the data we feed in to the machine learning model. We have the unstructured data, the data that have not been organized, and most times they are so large that we have called them the big data. What we want to get from this data is two basic things. The data on itself are some examples, some observation of the real world. But we want to learn something, some pattern from the data so that we can understand the attributes of this data, what this data represents. So some of the data that we use for machine learning projects that are very common and easily accessible on the internet today are, one is the IRIS data set that measure the sepal and the petal length. The MNIST, one of the earliest data sets that is used for handwriting recognition, Boston housing recognition data that we use for regression analysis. CIFA-10, one of the earliest image data sets. Movie review from IMDb data sets review. Or for the medical field, we have like breast cancer from the Wisconsin data set. We also have the popular ImageNet, which is one of the largest data sets in the world with over 1,000 categories, which is actually where most of the machine learning models are evaluated because it contains almost every category of object you can see in the world. We have the MNIST fashion, which is the fashion version of the MNIST dataset, MS COCO for object detection. For the surgical field, we have one of the largest datasets, Collect 80. And you also have the YouTube dataset, which, as you know, YouTube is one of the biggest source of data, especially in video formats. We have the IoT fish pond monitoring dataset, which Professor Collins Udano has introduced, generated by the HiPIC lab, which I encourage you to explore and see the data that has been created by this lab and see what you can do with it. Open Image dataset is one of the biggest datasets created by Microsoft. And we have the Yahoo Finance for those who are interested in the financial market analysis. Sentiment dataset, Sentiment 140 is one of my favorite because I use it for sentiment analysis, both in image form or sentiment that is contained in written data. Now, let's look at the data as a foundation of machine learning model. I decided to go through the back side of showing us what the data is so that we can begin to appreciate what data actually contain. And then we can see why it is actually the foundation of machine learning model. Machine learning model learns rules. The rules are the algorithm. It learns this rule from data. That rule that is learned is what we apply to new data to make prediction. So what it means is that with large data is like more experience. We have a good decision rule. But if you want to have a better decision rule, you don't just have large data, you have large, good quality data. So the quality of the data is important because it is like garbage in, garbage out. So let's look at the factors that could be affecting the quality of our data. The quality of the data directly impacts the performance of your deep learning or machine learning model. If you have poor data, your model performance is going to be poor, regardless of the algorithm that you use, regardless of how much you train it, because the data is what the model learns from. Once the data is not good, the model will not be good. And there are a lot of things that will make your data not to be good. For instance, incomplete data can make the model not to learn from the data. Incomplete data are data where you have some missing values or data that contain things like non-infinity in them. You have noisy data, data that have moved away from its original distribution. It contains some irrelevant information. For instance, if it is in the text or in the image, some form of corruptions, or it contains some special tags or characters or some formatting artifacts. You have the outlier, which are the rare or unseen terms that in your data that can make your data not to behave in a particular format. Like you can see in that image, I have a trend of data that follows a particular line, and then you have some data that looks like an outcast. They are not having the same characteristics as the data that you have. So we call that the outliers. We also have the bias. This is the data that is collected, formatted in such a way that it is having some bias in it. If a model is trained on such data, the model will be making prediction that is heavily biased. We also have data that are inconsistent. Their patterns are not following a specific pattern. There is variation, such as if it is text, you can have some unnecessary capitalization at some point, or you can have some unnecessary punctuation or some use of abbreviation or some jargons. We have also data that are outdated, data that at that time, they are not relevant. They contain information that are no longer true, or data that the quality is no longer okay. Broad data, corrupt data. One of the worst is having a non-expressive data, data that does not represent what you want to learn from the data. There are other ones like concept drifts. The data is good, but the concept is not there, or it is drifting towards something else. Or data that has a lot of distraction. You train the model to learn one thing, it will end up learning another thing because there are so much distraction. Apart from all these factors, there could be leakage in the data, which will make you think that your model has learned from the data, but the leakage is what makes it look like the model is performing well, but on unseen data, the model will not perform well. And the cost of obtaining data makes it difficult for us to actually have good quality data that our model can learn from. Now, what is a good data? A good data is a data that is accurate. A good data is the data that is complete. A data that contains information that is consistent over time. Information that you would not look for a pattern that deviates unnecessarily from what it should be. An information that represents what you are looking for. If you want to learn something from the data, what the pattern that should drive the model to learn that is contained in that data. A data that represents a real-world situation, a data that is relevant to the problem that you want to solve, a data that contains points from every aspect that is needed to be covered by your research. It's called an inclusive data. Such data your data need to be inclusive for your model to learn useful information. A data that is fair. Today, we are heavily on fairness in machine learning, a data that is also timely. You shouldn't train your model on very much outdated data. Now, what is the impact of having a good data? When you have a good data, you have a very low error rate. It means your model can make a very good prediction with high accuracy, contrary to when you have a very bad data, which is data that is noisy. And your model will converge faster. Convergence is your model finished training or finished learning. If your data is noisy, the model will be oscillating its learning and it will never learn. And here we say it finds a global minimum. So it will be navigating around this global minimum and it never find it if your data is not good. But if your data is good, your model converges to the global minimum very fast. It also helps with generalization. Generalization is where a model performs well on your data, and it also performs well in new and unseen data. So how do you make this, your data, a good data? Number one is a standard data collection. You need to be very careful with how you collect your data. You define a protocol that guarantees that the data you collected is of good quality. And you also do this by data pre-processing, which we are going to see in a couple of slides, and also clean your data. So let's look at data cleaning techniques or data pre-processing techniques. For me to discuss this, I decided to classify data according to their modality so that we can understand the common issues that are with this data, and it will help us with how each of these issues can be cleared from data. So first, we have the textual data, which is the text, the language data that you have, what you can type, what you can write. They contain common spelling error, grammatical error, inconsistent formatting. You can also find some ambiguity, noise, outlier, and missing data. We also have visual data, which is the data that you can see like images. This data can have issues with blurring, occlusion, lighting variations, some distortion. Even noise, outliers, and missing data can be found in images. Audio data are data with, you can find low signals, some prolonged silence, echo and reverberation, or some temporal misalignment. They can also have some distortion, noise, outliers, and some missing data. And we have the multimedia data, where we can combine most of these data together, like in the video data. So these data have a common, this common problem have a common way of cleaning the data. For instance, in the textual data, we can do text normalization. For instance, you have the raw data that are like this, inconsistent. You normalize them to give you a more clear data. We can do tokenization, which is like breaking your data into tokens or each words, creating a sentence into words. We can do stemming or lemmatization. Stemming is simply removing all the endings to have the stem or the root word. Sometimes the root word may not make sense. Lemmatization is combining it with normalization so that the root word have some sense. And how do you handle missing data? You handle this by some process, like either you are removing them completely, is the deletion, or by imputation, which can come through either averaging or some pre-processing, some prediction to discover what are the missing data. It is important that you don't train your model on missing data. Instead of that, it's better to remove the missing content completely. And then we also have the stop word remover. Here, what we do is to remove some points in the data that are not very useful to what we are doing, like this is a, we keep only the keywords that are essential for the understanding of the information in the data. The same goes to the visual data. There are a lot we can do. I summarize all this with data augmentation, where you can do the reduction of the noise, image cropping, different rotation, orientation, changing the contrast and the brightness, and flipping and removing the broadness and whatever that is in the data. For the audio data, we do a lot of it, cleaning it up, which I wouldn't want to go in, but standard things we usually use is what we call the Fourier transform, where we can do the time frequency transformation of this data to have a more clean data. So from data to feature, most machine learning algorithms do not take in data directly. They process features. But the process of this feature extraction is usually done by man. So we sit down, we write some code, we extract this feature. And when we have this feature, we give it to our machine learning algorithm to do the learning and do the classification. This is contrary to what we have in deep learning, where we make both the process of feature extraction and the classification to be learned by the deep learning model. So how do we move from this data to feature? Feature are the distinct measurable present qualities or attributes that we can find in our data. So these attributes, they may not look exactly like the data, but these are what the model easily understands. Most of the time, they are like numerical or categorical values. They are characteristics that are suitable for modeling. I will give an example of it in the couple of slides to come. So, but for us to move from data to feature, we do feature engineering. The feature engineering is the process of transforming unstructured data into the relevant feature that is needed. So we are given the data, we extract this feature through feature engineering, and then we can feed this feature to our machine learning model to learn from. And at the end, the feature that we extracted, not all of it are still very useful to our model. So we have another approach that we call feature selection, which is the process of choosing the most pertinent characteristics that we employ for our model training. So here we get rid of all the extraneous, pointless distraction elements in the data. So feature processing, like I said here, we transform our data to feature. Features are like numbers because our model cannot comprehend any other thing but numerical data. So it is necessary that we process our data, transform the unstructured data from text, video, photos into numbers. And these numbers are what reflect the relevant features that our model will learn from. And at the end, it gives us another feature, and we have a way of mapping this feature to the output, maybe to text or to another image or to whatever we need. So feature engineering, how do we do this? There are a lot of approaches. One of the popular one is discretization. So we have a continuous value, we convert it to discrete values. Another is decomposition. Decomposition usually applied to audio data where we want to extract the trend, the seasonal data, and the residual, which are the errors or the noise in the data. And we have the aggregation. In the aggregation, what we do here is to summarize our data, obtain some distribution that gives us the information about the mean, the mode, the standard deviation of the data, and feed this to our model. Then we have the feature scaling. Mainly we use the normalization or the standardization, similar approach, except just in the formula where one is subtracting the mean and the minimum from the data, one is divided by the standard deviation. So if you look at this image, you really understand the difference. When you normalize, the data is scaled usually between 0 and 1. When you standardize, it's usually between -1 and 1. So the mean is at the center. And when we have something like that, it becomes more meaningful. You can look at that and see how much the data is centered around its mean, and we can talk about its distribution easily. So with that, the model have less work to do than in understanding the features contained in the data. So there are many other ones like vectorization, tokenization, encoding, and other transformation, which I will not go into because of time. In terms of feature selection, what we do in feature selection is that we want to select few traits or characteristics that are helpful for specific tasks. Not every feature in the data is needed for a specific task. So we have to find and choose the most pertinent one for training of our machine learning model. Examples of where we do that is the recursive feature elimination, where we have to feed the data, get output from the model, project it to some space, latent space, and see some outliers. And with this, we remove those ones, feed the data again. Iteratively, we remove some irrelevant features from the data, and they give the model final features that are more relevant for learning the specific task. Correlation analysis is also what we do. We see how much the data are related to each other, and then we can remove the ones that are not related. Statistical tests, which we all know, is also another way to do feature selection, where we perform some student tests, some probability tests, and see which of the data are correlated, which of them should be considered. So this is all about what I can say about data, and I will be very quick with the rest of these, which are easier when you have understood the data. Going to the algorithm is the procedure or set of rules that we use to learn from the data. It defines the process of learning because we don't know the knowledge. So the algorithm is what the model follows to obtain the knowledge. So what we obtain with the algorithm will determine how our model generalizes to impute data. Examples of algorithms are like decision tree, neural network, support vector machine, and we'll see this later. So when you look at this image, we have the input and feature extraction, and the classification model here is the algorithm, and then it produces an output. There are types of machine learning algorithm. First, I want to classify this according to the task. If I'm classifying them according to task, we have the classification algorithm whose work is to classify data points based on the groups that they belong to, based on the categories that they belong to. The output is usually a distinct unique element, number, an integer number, or a unique number that is mapped to a class. For instance, the green class, the blue class, the red class, the different animals, so they are categorized. Whereas regression algorithms are the ones that learns to predict real numbers that can define a point. They are not defining a class, but they are giving a value. A very good way to understand this is from this example. If I want to look at the weather, if I am going to use a regression algorithm, I will be telling you what the temperature is or is going to be by tomorrow, and I give you a number like 84 degrees. But if I'm going to use classification algorithm, it's going to tell me whether it's going to be just cold or hot. So by classification. Another way to classify the machine learning algorithm is by the supervision, how they are trained. And here we have the unsupervised learning, supervised learning, and the reinforcement learning algorithm. There are other ones which I will not go into, like the semi-supervised learning, the weakly supervised learning, the self-supervised learning, active learning, incremental learning, few-shot learning, meta-learning, and the rest of them. So, but today we are going to focus on just these three. For the supervised learning, it simply means learning from the label data. The label data is the teacher. So in this case, we give our machine learning algorithm a pair, and this pair is the data point and this label. And the label contains the desired solution that we want to achieve. So what the model does is to learn this solution from the data, and is trained, or is the teacher is making a correction based on the label. So if that label is a real number, we are doing a regression. If that label is a discrete number, we are doing a classification. And some examples of classification, example of supervised learning is spam detection. You get an email, your Gmail is able to classify it as spam or not. Or you want to classify fruits like I have in this image. Example of regression supervised learning is predicting like the price of house, maybe next year, the price of the petrol in next year, or the price of the stock at the close market price. Some examples of supervised learning algorithm, we have the linear regression, one of the most important. It learns a trend that helps to make a future prediction. So if I learned the pattern in the data over a series of experience which are contained in data, I could predict what the next data would be. We have the logistic regression and advancement of this linear regression, and we also have the decision trees, the random forest. The random forest uses a decision boundary that is learned with W times X minus B. I will not go into explain what each of these mean, but you can ask me a question on it after I can explain that. And then we have the k-nearest neighbor that try to understand, given a data point, where it belongs by trying to measure its distance from known categories. And then we have the naive-based model, which is built based on the Bayesian algorithm, which is one of my favorites because you use probability approach to learn from the likelihood and the prior probability and the evidence to know what the posterior would be. We also have the regeneration regression and the neural networks. So with this, we can look at unsupervised learning. Unsupervised learning, there is no teacher. So you are not supervised. It means you are learning without label data. In this case, the model tries to learn by trying to discover the pattern or the structure on its own. Maybe this pattern can be the color or the textures that are in the data. It tries to cluster them, try to learn by reducing some dimension or some visualizing what is in the data. And at the end of this, it learns something that could help you to make prediction in future. A very good example is customer segmentation. Based on what your customers are buying, we could group customers that are having the same test together. Some of us goes to social network and you begin to get some ads. The ads are targeted because they are clustering your activities, and they could see what people who perform the same type of activity you are performing on social network usually go for, and they try to suggest such ads to you. So this is what unsupervised learning looks like. Example of unsupervised learning algorithms are the k-mean clustering, which is one of the fundamentally used. It's try to create a centroid, cluster the data around this centroid, and try to model them, separate them, and give these clusters a name in terms of maybe a group name that represents the classes. We can also do this hierarchical, and call this hierarchical clustering. The principal component analysis is one of the widely used because it tries to separate these to their orthogonal dimensions, and then we can see some parent point that helps us to understand the patterns in the data. Fisher discriminant analysis is an advance of this. And one of the ones I love most is the T-distribution stochastic neighbor embedding, which is the TSNE. It helps you to separate a lot of data points, and you can see the pattern in the data. The autoencoder is with the use of neural network. Here we try to reconstruct the inputs as the output. And by so doing, we learn some pattern that the model will learn that helps it to reconstruct this original input as the output. We have the reinforcement learning, one of the widely used, especially for training agents and the robots. So in this case, we create a system we call the agent. The system observes its environment, performs some actions, gets a reward. So this reward can be positive or negative. If it performs well, it gets a positive reward. If it performs wrong, it gets a negative reward, which is punishment. And by trying to avoid negative reward and maximizing positive reward, the model begins to learn the best strategy we call policy that helps it to get the best reward over time. So this policy defines what action the agent should choose when it is in a given situation. And it has been used very widely in creating a lot of machine learning algorithms. Notably is the AlphaGo that has beat a lot of experts in playing games. It is widely used today in robotics navigation, and there are a lot of other things that we do even in the deep learning. Reinforcement learning is also used there. A very good example of what reinforcement learning looks like is if I have an agent, it has to go in two directions, any of these two directions, either to the fire or to the water. If it gets to the fire, it gets some heat, so it loses some point, and it doesn't want to lose some point, so it knows that going to this direction is a bad decision. So it updates its policy, and then it can make a better decision in the next iteration. Another way is for a baby who is learning to crawl. If it crawls some step, you give it some milk. So for it to get some milk, it needs to crawl more steps, and then it's learning how to crawl. Some reinforcement learning algorithm, which I will not go into detail because of the time, include the Q-learning, where we try to learn the table that helps for the action and the state of the action at each time. The deep Q-learning using the deep learning approach to learn this Q-table. And the policy gradient method, the autocritic method, and the horizontal policy optimization. If you have questions on any of this, you can ask me during question time because I think we're already behind the time. Now to the model, the last part of this machine learning component. So what is the model? The model is what we learn by training our machine learning algorithm. It is the final output that results from applying an algorithm to the data. So the model represents the learned pattern. It represents the relationship. It represents the weights, represents the information that the model will use in making decisions. So when we give it a new data point, it makes a decision based on the model. So when you create a machine learning algorithm, you train it, you get a model. This model is possibly what is sold or what is deployed for people to use a machine learning algorithm. Now, this model can come in different ways. Depending on how much you have built and trained it, it can be an underfitting model. An underfitting model is a model that has high training error. It means that the model has not learned anything. It's either that the model is too shallow to learn, or the data is too much for the model, or there is high bias in the data. Then we have if you look at the image here, for the regression model, you can see that the hyperbole, that is the decision boundary, is not classifying anything in the regression. It's not following any pattern. In the classification, it is not separating the classes. And then the just right model is a good model. The model that you have trained is an optimal model. There is less training error, and this training error is also less in the test data. So this model has a very perfect curve in terms of your regression, and it can also separate the classes with less error. But when you look at the overfitting model, this is usually the biggest problem we find with machine learning. Here you have a low training error because you are training, the error is reducing, and you think your model has learned. But when you test it, you have high error. This is usually because of high variance in the data, and a lot of things can cause it. Maybe the model is too complex and the data is too small that the model has memorized the training data and is giving you the correct answers of the training data because it has memorized the training data, but it cannot generalize on unseen data. So you can see the pattern, it fits almost every point in the regression. It tries to classify every point, including what could be an outlier. And with this, it cannot do well in the unseen data. So we go over to model selection. When you have model that is either underfitting, overfitting, or right, how do you know it? How do you select the right one? Model will either overfit or underfit because there is usually something we call the bias or the variance in the data. If the bias is low, the model will underfit. If the bias is low, the model will not underfit, it will overfit if the bias is high. But if the bias is low, the model will not underfit. But if the variance is high, the model will overfit. So we need to keep both the bias and the variance low, and this is usually impossible. So we need to strike a balance, and this striking a balance is what we call the bias variance trade-off. So how do we strike this balance to find the balance between our bias and the variance in the model, and so that we can get an optimal model from our trained models? There are several ways we can do that, but the commonest is through validation process. So the first is we need to avoid overfitting. And when we avoid overfitting, we reduce much of variance and the bias in the data, and we are close to selecting the better or the optimal model. And to reduce underfitting from our data, first, we need to make our model more complex. If it is too simplified, we need to add more feature that it can learn from so that it doesn't learn from simple, small features that doesn't represent the word problem. We need to train more. To avoid overfitting, we need some validations. We need to check if the model is learning what it's supposed to learn at every time. And then we need to perform some regularization, which is a way of penalizing a large weight so that the model does not look for shortcuts. We need to also get some more data. We need to augment the data we get so that the model can see more examples, more different scenarios so that it can generalize. And we also add and remove some features based on the performance of the model. So how do we perform all this? We do this by making predictions. You train, you make a prediction. You analyze these predictions to check if your model is doing well. And to analyze this prediction, you interpret their model. Interpreting the model goes towards what we call explainability, which is not part of what I'm going to explain today because I noticed it's in one of the topics for next section. So when we do prediction, what we do is that we give our model, which has been trained as a black box, we give it a new sample and it makes a prediction. And then we compare that prediction with the ground truth, what should be the output. Now, when we have had that, we do this we evaluate the performance of that model and say if our model is doing well or not. For us to do that, we need to split our data into three. Usually, we have the training set, which is the set of data where we train our model. Our models should only see this training data. And then we have the validation set, which is a small set of data where we test the performance of our model over time. And from this validation set, we tune the parameters of our model, the hyperparameters of our model, so that we can select the best model based on this validation set. And the test set is the sample that the model never sees. This is the sample data that we keep out from the training data. We call it the unseen data, because this is where we are going to evaluate the model and get the true performance of the model. And this also represents how the model will do in the real world after you have deployed your model. So, in terms of evaluation, we are measuring the performance. How do we measure the performance? We measure either the accuracy of the model, especially if you are doing classification tasks. We also measure the error in the model if we are looking for the regression types, and the example of what we can measure is the mean square error or the mean average error. We can also measure the precision of our model or the speed for those that are doing higher tasks like tracking and the rest of it. So these metrics are not that straightforward. If we have a real-world sample that is positive and negative, our model makes a prediction, which is like the circle, the red dot circle in the middle. If that red dot circle represents a positive prediction by our model, the part that intersects with the real-world positive is called the true positive. The parts that are positive, which our model did not classify as positive, is the false negative, because the model says it's negative, but it is positive. So it is a false negative on the model. The part that is negative, but our model classify it as positive, is a false positive. The model says it's positive, but it is false. So it's a false positive. Whereas the part that is negative, which our model did not classify, which means our model says it's negative and it's negative, that part is true negative. So we are dealing with 4 quantities, and understanding this puts a lot of confusion. I think that is why we have something we call the confusion matrix that helps us to describe the performance of our model on the set of our test data to understand the true value, whether it is saying that something is positive where it is positive, or that it's positive when it is not positive, or it is negative when it is positive, or it's negative when it is negative. So these 4 quantities are important, and we put this in a table to learn either type 1 error of our model or the type 2 error. And with this, we can compute what we call the precision or the recall of our model. We can also put this in graphical form, learning either the precision recall curve or the ROC curve, which is the receiver operator characteristics that define how good our model is. So ideally, we want to get the top curve. As it's close to 1, we have a model that can perform very well in unseen data. A model that will not misclassify, a model that will not give us false alarm. So when we have this matrix, we can perform a type of validation we call cross-validation. I have explained before that we split our data into training, validation, and test. So we validate on the validation set to select the best model. But also the validation set can be biased because it's a small sample. It may not represent everything in the train set. It may not represent everything in the test set. So we have something we call cross-validation. What we do here is we split our data into fold. For instance, 5 fold here. We call it K-fold cross-validation. And then we train on 4 fold and validate on 1 fold. After that, we train on the other 4 fold and validate on another 1 fold. So we iteratively change our validation set. At the end, we have a validation across the entire data, and we can take the final evaluation to represent the performance of our model. So K-fold cross-validation is a very good way of validating our model and selecting the best model from our machine learning model. So it is actually called one of the best model selection approach. Now, getting started with machine learning. After hearing about everything, how do I start if you are not in machine learning? The first is understand that machine learning is built on mathematics and probabilities. You need to learn a lot about statistics, the distribution, the probability, and also the linear algebra. There are a lot of libraries that helps you to get started, like the NumPy and the SciPy. Then programming is part of machine learning because you have to actually code the algorithm or the steps that the algorithm should follow to learn the model. So you need to learn the data structures. You need to know about the object-oriented programming, how to structure your algorithm. You also know to parallel programming. We can learn this using Python code. There are other programming languages we can also use, but Python has proven to be the best so far. You need to know about the database system because you need to structure your data. Either you are structuring it with that SQL, structured query language, or no SQL. You also need to know these machine learning algorithms like the regression, the classification, the clustering algorithm. You need to have the foundational knowledge of them. And then you need some machine learning tools. The popular ones are the scikit-learn, TensorFlow, PyTorch, and Keras. So when you have these 5, you are good to start. And there are a lot of resources online that can guide you step by step on using this to build your machine learning algorithm. So having said that, what are the real-world applications of machine learning? One of the earliest applications that we did in my research lab was to apply machine learning in healthcare. We don't really use machine learning today, but we have used it at the early stage for the personalized surgery. Here we built a hidden Markov model, which is one of the strong, powerful machine learning algorithm to learn surgical workflow analysis. And we can use this also in finance for fraud detection and the algorithmic trading. I think this is one of the biggest paying industry in terms of use of machine learning. So we can predict the stock markets. One of the earliest work that was done by Peter used some combination of expert systems and some machine learning. Here he combined some support vector regression model and the random forest and some artificial neural network. And they were able to predict the stock market index with the fusion of these machine learning algorithms. And if you are doing a course in machine learning, you will definitely come across the IBM Watson, who beat the champions at the Jeopardy Game Challenge. And this is done using machine learning techniques. And then the recommendation systems that we see today in our social network recommending advertisement has been used to actually win 1 million prize at Netflix competition using machine learning algorithm. Beyond this, we can use machine learning for a lot of things, for our crop yield prediction in agriculture, pest detection in agriculture, in transportation for autonomous vehicles, and for route optimization, transshipment programs, and the rest of it. E-commerce, like recommendation system I have talked about, or for analyzing the customers' behaviors with your machine learning analytics models. So with this, and with also because of time, I want to conclude the talk by looking at what we have discussed so far. First, machine learning as a branch of AI that is concerned with learning from data. We discussed the foundation of machine learning, which we have seen as data. The data having the knowledge, data having everything that we need. We looked at how we can move our data to feature. We can transform it to feature for our machine learning to use it and the various data pre-processing techniques that are useful for achieving that. We look at some fundamental machine learning algorithms, their supervised techniques and everything around it. And we look at how we can make our model prediction and evaluate the performance of the model for better model selection. And we have seen some real-world applications of machine learning. But the trend of machine learning continues. Some of the emerging technologies are the auto machine learning, auto ML. I think this is very useful for one who doesn't have foundation or background in machine learning or programming, because here it allows you to use machine learning without explicitly knowledge on machine learning technologies or programming skills. You just have to use it because the frameworks have been provided by some big tech companies like Microsoft, Google, and the rest of it. We also have federated learning, which is a way of training machine learning models from different centers and averaging the weight at the server. We also have the growing interest in the ethics in machine learning, the fairness, the transparency, the accountability, explainability, and the rest of it. And this comes to play because the world has started realizing that the data is a very strong resource. And so there must be need for transparency, fairness, and accountability in the use of data. And also the transition from machine learning to deep learning. Because at this stage, we learn more complex patterns and relationships that helps to explain real world better, even more than the human brain. So with this, I always like to present this question, which almost everyone asks me each time I make a talk around machine learning, deep learning, AI, and the rest. Can AI replace me at work? And to me, I think so far, what I can always reply is that the AI will actually will not replace you now, but those using AI can replace you. So this means underscore the need for knowledge in AI. So with this, I say thank you for listening.
Wow, thank you very much, Dr. Chinedu Moye. This is a very, very, very good way to start. I told you, ladies and gentlemen, that you have come to learn. Like this is just the beginning. We have a lot in stock for you in this webinar, and it is well packed, fully packed for some of you that will are in machine learning career or want to join in the career. I must say once again, thank you very much for bringing this expose of the introduction of machine learning. There's a lot to learn, and you have really, within the shortest period, touched a lot of things for us to, begin to ponder with. At this point, I want to see if there is any question from the audience. We can start from that. Then I must first of all apologize to everyone because we are supposed to have ended in the last 30 minutes. We did start on time today. Normally, it was supposed to end just it's supposed to be a 1-hour discussion, but it is what it is. We don't regret the time that we spent here today. It's actually worth it. Machine learning has actually been a very interesting area. As you can see, there are a lot of things we can actually do with machine learning. The application area is also it's very pronounced in different area. You can apply it. You also have also seen that you don't have to be a computer scientist or an engineer or someone who is a data scientist to start learning these things. It can be applied in any way. And the question about AI taking your job, well, you have heard from the horse's mouth. AI is not here to take your job. However, the people who are using AI may likely take your job. So if you are still waiting, then you might be caught up in the middle of the road one day. Do we have questions now? I'm only seeing thank you, very great, awesome. Okay, thank you very much. This is okay. This is Chinedu Akamobi says, thank you very much, Dr. Chinedu. God bless you. You kept my mind wide open. Okay, it has been also. Thank you, Dr. Moye. Wow, this is interesting. Okay. All right, there's a question. This is Mangoba from South Africa. It says, how does one decide between a SQL database such as Microsoft SQL Server and no SQL database such as MongoDB for storing your data for a machine learning model? How do you decide? Is that the question? Okay. I will leave it for Chinedu to answer, although I know the answer, then maybe I'll add from there. Okay, Dr. Chinedu, if you're there, the question is for you. It says, how does one decide between an SQL database, such as Microsoft SQL Server, and a no-SQL database, such as MongoDB? How do you decide which one to use for your ML data?
Thank you so much for the question. It's a very interesting question. The simple answer would have been that it will depend on the data, but that's not enough, because when you have structured data, you likely go for structured database like SQL. When you want data that you can easily access, like that are not structured, you go for non-SQL database. But that is not enough for machine learning. So there are a few things to consider for your ML. Usually, how machine learning works these days, we usually try to keep it in a way that we can feed the data, but usually this decision is made based on training speed so that you can train your model fast and make inference fast. But that is not enough. So I would say, if you want to choose SQL-related data, best is when you are dealing with structured data that follows a particular schema. It has complex relationships like foreign keys, joins. It has to deal with probably tabular data where the rows and column follows a rigid format, where you kind of think transactional system and traditional businesses. You use SQL if this data is structured. The machine learning relies on the features that fit well into what I showed in one of the slides, into columns where you have attributes and the observation. But then non-SQL, it is suited for semi-structured data and some unstructured data, like maybe documents that you stored, example, like what you can keep in your MongoDB, or key value stores like Redis, wide column stores, things like Cassandra's data, or you want something like graph database, things that are not really structured. So you use non-SQL if your data is unstructured, semi-structured, or contains some nested fields. But that's not all. You use it also for scalability. Scalability here is that relational database generally scale vertically, I would say. So they increase, you're increasing server capability here. So what it means that when it can become expensive, I think you should go for SQL. However, some SQL database like PostgreSQL offer you horizontal scaling through shading. So when you have this, it can help you to add the complexity of the data. So you use SQL data if the data is moderate in size and the relationship query are critical for your model. But you use non-SQL if you are working with large distributed database and you need the scalability storage for high velocity, high volume data. That is the second reason. Third place is your query complexity can also determine this. If your relational data is usually ideal for complex queries where you have aggregators, join, I think multi-table queries, all these that are needed, if you are needed all this for your feature extraction and your data pre-processing. So you need to use SQL to perform this complex query for your machine learning training, especially if the machine learning, if the machine learning training, the relationship in the data between the database are very important in your machine learning training. Otherwise, you use your NoSQL data if your queries are simple and if the focus is probably on speed rather than complexity. So there are lots of things. You can also like consider it in terms of the volume. You can also consider it in terms of your consistency and the availability of the data. You can consider it in terms of your data relationship, in terms of the transaction management in your data. You can consider it in terms of the data pre-processing pipeline for your ML, in terms of the use case considerations. So there are a lot of things that you consider to make all this. I won't give you exhaustive list of it now because it is like an impromptu question, but I think I gave you some information already.
Thank you very much. There's another question here that I want to read for you. The question says, how can too much data affect machine learning model? Just within 20 seconds.
Okay, yeah. One of the graph I showed.
This question is from Gregory Anichebe.
Okay. First of all, I will rephrase the question a little bit so that it can fit the answer. So it is not ideal to say that too much data affects machine learning. Too much data can affect the machine learning you created based on the complexity of the model. If you have created a simple model, you shouldn't use too much data to train it because the model may not be able to handle the complexity in the data. But if you have much data, I think you should go for much complex model. There is no amount of data you have that we can create a machine learning model that can learn comfortably from it. So then the graph that I presented before, I showed the learning curve. There is a time to plateau. That is when learning probably kind of saturates. You don't really learn something more meaningful. Now, when you are giving more data to it, it doesn't really affect the model negatively. But what would be the right question is too much training. So if you are giving it data, if the model is being used to retrain the data is used to retrain the model over and over again, you get to a point when it has learned all it needs. and it start to, if you continue to train it, it start to learn some variance in the data, and this start to lead to overfitting. It start to learn some features that are not relevant.
All right, thank you very much, Dr. Chinedu. Apparently, what he said right now is that data, machine learning actually fits on the more data. The more you feed data to your model, the better. So don't make that mistake and think that you don't have to, put in more data. More data actually helps your model to perform well. However, the choice of model data is also very important depending on the kind of data you're working on. So there's another question from Chinon. So I'm going to read only 2 questions remaining now. Then we'll take it off from there. Chinon also says, expert systems machine learning? Also, is machine learning a part of AI, or is it the AI itself? I'm kind of new to this concept mentioned here. So what's your take on that?
Yeah, one of my earliest slides actually touched about it. Maybe I should go back to it to show you.
Yeah, so I think we're going to share the recorded.
Okay, yeah. So AI is the broad field, yeah, and AI has a lot of subdomain, and one of these subdomain is machine learning. Expert system is also another of these subdomain. So both expert system, machine learning are all subdomain of artificial intelligence.
Great. Thank you very much. I guess that answers that. The last question here says, is from Okechukwu Nebedumi. Says, thank you, Dr. Warrior, for this impactful lecture. Can we have the recorded lecture? Okay, we're going to have the recorded lecture so we can properly digest it before next lecture, especially for some of us who are coming from the geoscience world and have no AI background. Okay, so this the recorded video lecture is gonna be made available to everyone, and I think the registration people put in their email addresses, so that is gonna be used to forward the recorded video. Okay, so I think with this we have done justice to it. I apologize again that we took your time. We were supposed to have ended earlier. We agreed that it's going to be 1 hour lecture. However, we have seen that it has gone beyond 1 hour. But on behalf of the team from HiPIC and some of us at this part of the world, including the speaker, I will say thank you, everyone, for coming. Make it a point of duty to come same time, same link, next week, Friday, for yet another interesting talk. But before we go, Professor Collins, are you there? Can you share the? Can you stop sharing? Can you share our next speaker, please? The poster. All right. Could you confirm if you can see my screen, please, everyone?
Yes.
Okay. So next week is going to be data governance, and this data governance is where we are going to be learning things about data collection and privacy, that best practices for data collection, how to design effective data collection strategies, and how so to ensure data quality and reliability. In terms of data privacy and security in AI, we're going to be talking about data privacy concerns and regulatory frameworks. We're also going to talk about techniques for ensuring data security. So this is an opportunity for you to come and grab this knowledge. Our speaker is going to be is a CEO and a founder at HiPIC in South Africa, and he's going to be joining us next week, Friday, same time, 5 o'clock Nigerian time. So with this, I will say thank you everyone for coming, and see you next week. We're going to make the videos available for all of you. Thank you. And please make do and follow us on our social media handles. Follow HiPIC on social media handles.